Measuring the speed of light. In the 17th century it was believed that light could travel any distance in no time at all, that it had infinite speed. However, Galileo carried out an experiment to attempt to measure the speed of light. He placed himself on a mountain with a shuttered lantern, and had an assistant on another mountain, also with a shuttered lantern. The two mountains were a known distance apart. The idea was this, that Galileo would send out a pulse of light. As soon as the assistant saw this pulse, he would send out a returning pulse of light. All Galileo had to do was measure the time taken for the pulse to return, and then calculate the speed of light from speed is equal to distance travelled divided by time taken. However, the time taken was just too short to be measured in Galileo's day. Evidence for the finite speed of light came from the Danish astronomer Ole Rømer, who discovered that the moons of Jupiter altered their speed of orbit slightly depending on the position of Earth relative to Jupiter. This diagram and those that follow are very much not to scale, they're just to get across the idea. Jupiter and Earth orbit the Sun, something like this, and so the distance between Jupiter and Earth varies significantly depending on the positions of the Earth in its orbit and Jupiter in its orbit. So, for example, in this position the Earth and Jupiter are relatively close to each other, and as the moons of Jupiter pass round the back of it, round here, light reflected off them travelling towards Earth would follow this relatively short path. Sometime later the Earth and Jupiter may be in these positions, so as the moons return round the back of Jupiter, the path that the light travels is much longer. This caused the moons of Jupiter to appear to slow down as the Earth got further away. The moons appeared to speed up again as the Earth was getting closer to Jupiter. Rømer was able to calculate that light took around 22 minutes to cross the Earth's orbit, but he didn't at the time know what distance this was. Later, with a known distance of the Earth's orbit, Huygens was able to calculate the speed of light very accurately. Many other methods have been used to find even more accurate values of the speed of light over the years. The basic problem is one which appears in many experiments. When measuring something very small, any uncertainty in your measurement produces a large percentage uncertainty. In a very simple analogy, marathon times tend to be quoted to the nearest second, whereas the 100-metre sprint times are quoted to the nearest hundredth of a second. The much shorter times involved require much greater precision of measurements.